Welcome. The physical design process is divided into many sub-steps. The first sub-step among them is circuit partitioning. So we said that at the end of the logic design step, we will have a circuit design consisting of millions of cells, macros, gates, transistors and their interconnection. Now, we have to place this entire circuit design into a single chip. So we have millions of transistors on a single chip, and it is not feasible to lay out the entire chip in a single step. Hence, to control the complexity of the design process, we partition the circuit into sub-circuits or blocks. The output is a set of blocks and interconnections among them. So the output of the partitioning process is a set of blocks and interconnections among them. Partitioning can be hierarchical, blocks can be divided into sub-blocks. Okay. So, partitioning is the process of decomposition of a large system into independent manageable subsystems which can be designed independently and concurrently. The input to the partitioning process is a set of components or modules. These modules are the cells, macros, transistors, gates that we have been telling, and a netlist in the form of a weighted graph or hypergraph. Nodes represent modules and edges or hyperedges represent a net or an interconnection. And what is the output? The output is a set of sub-circuits that when connected function as the original circuit. So after partitioning, the function must be preserved. The function that was performed by the original circuit design should be preserved even after partitioning. The terminals required for each sub-circuit to be connected to other sub-circuits also needs to be defined. So now when we have partitioned and defined the blocks, we know how many wires will cross the boundary of the partition and will go to blocks in other partitions. Now therefore, these wires that cross the partition and go to other partitions can only go through to the other partitions through terminals in this partition. So therefore, at the output of the partitioning process, we also know the terminals of each partition. The partitioning process will be carried out under certain constraints. For example, there can be a minimum and maximum bound on the area of each partition, on the number of terminals, etc. So now we come to levels of partitioning. First, we have the system. The entire circuit diagram will consist of the entire system. It will be divided into a set of PCBs in the system level partitioning, where each PCB will consist of similar functions. These PCBs again will be divided into a set of chips at the board level partitioning. So more similar functions will be partitioned into a single chip. So therefore, a set of chips will compose a PCB. And then a chip is divided into sub-circuits or blocks, and that is called chip level partitioning. This is a representation of a hypothetical circuit design. So here are the modules of the circuit, here are the interconnections or wires. And we said that we have cut the circuit into two partitions. So this is partition 1 and this is partition 2. Partition 1 consists of these two modules and partition 2 consists of these three modules. And there are wires that are crossing the partition, right? And this line will be called a cut, right? And here we see that there are two lines that cut. So these are the two partitions that we have. After the partitioning process, these will form two separate blocks, block 1 and block 2. And the size of the partition, one of the important parameters by which a partition is characterized is the size of the cut. So there are two wires that cut through the partition, and therefore the cut size is 2 here. So an important partitioning algorithm is the Kernighan and Lin algorithm. So how does the Kernighan and Lin algorithm work? It starts with an initial partition generated randomly, and it moves components between partitions to improve. So it is a group migration based algorithm, and it is an iterative improvement based algorithm. It iteratively improves over phases. The Kernighan and Lin algorithm solves the following problem. The input consists of an undirected graph, the netlist, consisting of 2n vertices. Therefore, we have 2n circuit modules and m edges between them. So, there are m interconnections or wires connecting the circuit modules in this graph or netlist. And we also know the cost of each edge. The cost CAB of each edge AB is known to me. This is the input to the problem. And the output, what do we desire out of the Kernighan and Lin algorithm? We want to obtain two partitions X and Y such that the total cost of the partition is minimized and each partition should have n vertices. So we want to obtain two equisized partition of size n from the entire circuit consisting of 2n circuit modules. The Kernighan and Lin algorithm starts with an initial bisection P equals to x comma y. So x is one partition and y is the other initial partition. So initially we will randomly choose n vertices and put in x, and other n vertices and put in y, and get an initial partition. And that initial partition will have a cost in terms of the number of wires that cross the partition, that will be called the cut size. Then we proceed in steps. So first we choose a pair of free cells, A belongs to X and B belongs to Y, such that exchanging A and B gives the highest gain in terms of reduction in cut size. So we choose two modules or vertices, and one from X and the other from Y, and exchange them. How do we choose these two vertices? We choose these two vertices such that these two vertices after exchange will give us the highest gain among all vertices in X and Y in terms of reduction in cut size after their exchange. So then we actually exchange A and B tentatively. We actually exchange A and B tentatively and then lock them from further consideration in this loop. So after we have exchanged A and B and have locked them, we cannot consider them for further exchanges in subsequent iterations within this inner repeat loop. We note the gain Gi corresponding to this exchange of A and B, and we do the same thing until all pairs are locked. After a pass within the inner repeat loop, we unlock all vertices, and then we find K such that G equals to G1 plus G2 plus Gk is maximized and actually exchange cell pairs up to this kth step. So what do? We find a K. We start from 1, the first exchange, second exchange, third exchange, fourth exchange. We go on taking these exchanges until what? Until we get the highest gain. We have to remember that many of these gains will actually be losses. That exchanging them did not provide me a decrease in cut size. It provided me an increase in cut size. Therefore, there will be a certain step K up to which we will have an effective and maximum increase in cut size. Effective and maximum decrease in cut size. And beyond that, we will not do exchanges. So in this pass, we will do actual exchanges up to the kth step and then repeat this in the next loop. In the next loop, we will again find a pair of vertices starting from those which provide me the highest gain and go on doing this until we have a pass when we do not have any gain at all. firstly we need to understand how we choose vertex pairs and exchange them. So we said that at any point in time we choose that vertex pair that gives me the highest gain. So how do we define a gain? The gain is defined as dA plus dB minus 2 CAB, where CAB is the weight between A and B. So it is the cost of the edge A comma B. So what can this cost of the edge A comma B denote? It can denote, for example, the number of wires that interconnect the two blocks A and B. What is dA? dA is given by in A minus out A. So what is in A? In A is the number of edges that are incident on A and do not cross the partition. And what is out A? The number of edges that are incident on A and cross the partition. Okay. So out A equals to total weight of all edges of A that cross the bisection. In A, total weight of all edges of A that do not cross the bisection. So now let us see the values of dA for this node, say here 5. So we see that it has an in A, in of 5 is 1 and out of 5 is 2. So dA, which is d of 5, will be 1 minus 2, which is minus 1. Let us take another node 3 here, for example. 3 has an in edge of 1 and there are 3 outages. So therefore d of 3 is 1 minus 3, which is minus 2. Now let us say this pair gives me the highest gain among all pairs that we can consider, right? This pair gives me the highest gain. And then we exchange these pairs. So what happens? Whatever was an in edge becomes an outage, and whatever was an outage becomes an in edge now. So 5 goes this side, 5 comes this side. Now what happens? Its outage will be 1 and its in edge will be 2. So the changed dA value will now be plus 1. Now when 3 comes to this side, its changed in edge will be 3 and its outage will be 1. So in edge minus outage will be plus 2. So the total gain will be 1 plus 2, which is equal to 3. If we consider another vertex pair, say 6 and 3, before it is exchanged, 3 had an in edge minus outage dA value of minus 2. Similarly, 6 also had a dA value of minus 2. It has 3 outages and 1 in edge. So in edge minus outage is minus 2. So now what happens? When 6 comes this side and 3 comes this side, on this side 6 dA value changes to plus 2 and 3's dA value also changes to plus 2. So 2 plus 2, the total gain is 4. However, this edge that connects 6 and 3, we need to decrease the cost of this edge. So the gain has to be decreased by the cost of this edge, and that is also twice, once for 3 and once for 6. 3 was an outage for 6. When I took it to this, in the dA value we considered that 3 has become an in edge, but because 3 has gone on the other side, 3 is still an outage. For 3 also, 6 was an outage, and after the exchange, instead of becoming an in edge, 6 still remains an outage because 6 has crossed over to the other side. And therefore, we need to subtract the cost of CAB twice to get the actual gain. So we have chosen two vertices A and B. We want to find out what is the gain after exchanging them. So how do we find that out? We find the gain after exchanging A, we find the gain after exchanging B, and if A and B, these vertex pairs, are connected through an edge, we need to deduct the cost of the edge from the total gain twice. This is what this gain a comma b says, right? So now we see the steps, one step in this loop. So what are we seeing? We are seeing this one, these set of steps. This inner loop we will see. So first is to choose, first we see that the cut size is 9, the initial cut size is 9. So first we choose a pair with the highest gain. Firstly, we have to keep the vertex gains for each vertex pair in a separate table. 3, 6 gives the highest gain, say. So we saw that the gain by exchanging 3, 6 is 3, and therefore the cut size reduces by 3 and the new cut size becomes 6. After that, the highest gain is provided by the vertex pair 4, 6. So we choose 4, 6, exchange them and see that the gain produced now is 5. So previously we see that the maximum gain was 3, but after 3 and 5 has been exchanged, the new gain that is provided now is 6, 4 is 6, 4, and the gain is 5, which is higher than the first gain, right? And then the cut size reduces to 1 from 6. So 6 minus 5 is 1. Now the next two vertex pair, the gain is negative. It's minus 6 and minus 2. However, we have to continue doing this until all vertex pairs are exchanged in the inner loop. And then we said we only take up to that gain, up to that value of k, which provides me the highest gain. Here we see that the value of k is 2. So after these two steps, we do not get, the highest gain is provided only after these two steps. And hence we only take up to these two steps, right? And in fact, for this example, we need only one pass. In the second pass, we will see that none of the exchanges gives me a gain which is higher than 1. The lowest cut size that is possible is 1, and in the second iteration, g will remain equals to 0 and the algorithm will stop. What is the complexity of this algorithm? The complexity of this algorithm is big O of C and Q, where n is the number of vertices and C is the number of passes. Okay. So why is it n cube? Because initially we need to separately calculate the d values of each node, and that will take big O of n time, right? So to calculate the gain value, each calculation of each gain value for each node takes constant time. For n nodes, it takes big O of n time. Now within each pass, we need to compute the gain across all free pairs. Now in each pass, we have to once calculate the gain across all free pairs, and then we have to go on updating the gains in each pair. So what is the maximum that number of pairs that we have to choose? It's big O of n square, right? We have n vertices on one side, on one side of the partition, n vertices on the other side of the partition, and then we have to take one vertex and find the gain with respect to all other vertices on the other side of the partition. Then we take another vertex on this side and find out the gain for all vertices on the other side. Likewise, we will do for this step will be done for all vertices over all vertices in a partition, and hence the total step, the total computation that will be required is big O of n square. The number of passes is usually small. What are the drawbacks of the Kernighan and Lin algorithm? It only considers unit vertex weights. It's not applicable to hypergraphs. We will not define hypergraphs here. Basically, we can say that hypergraphs is related to the representation of nets that can be connected to multiple blocks, more than 2 blocks. So multi-terminal nets can be represented by hypergraphs, but we will not consider hypergraphs here. Partition sizes have to be pre-specified. We can only do a bipartition of equal size, and this is high time complexity. It's big O of n cube. However, many of the algorithms in partitioning are extensions of the Kernighan and Lin algorithm, or use the Kernighan and Lin algorithm in its various internal steps. We will look at a few extensions to the Kernighan and Lin algorithm. First one is that how do we get unequal sized partitions out of the Kernighan and Lin algorithm? To partition a graph with 2n vertices into two subgraphs of unequal sizes n1 and n2. So what do? We divide the nodes into two subsets A and B containing minimum of n1 and n2 and maximum of n1 and n2 vertices respectively in these two partitions. So initially during partitioning, what we will do, one of the partitions, say A, will contain min of n1 and n2, and on the other partition we will keep the max of n1 and n2 nodes or modules. Then we apply the Kernighan and Lin algorithm, but restrict the maximum number of vertices that can be interchanged in one pass to a minimum of n1 and n2. So now we need vertex pairs in n1 and n2. Because the number of nodes in these two partitions are not same, we can only exchange to a minimum of n1 and n2. So what will happen to the other nodes? They will be not considered in this pass, and they are remaining only because they formed pairs with other vertices which produce very less gain. Only because of that they were not considered, and they can be considered in further subsequent iterations. In this, so within each iteration we will only consider a minimum of n1 comma n2 vertex pairs and actually exchange them and consider them for exchanges. The next extension to the Kernighan and Lin algorithm is to generate two-way partition of a graph whose vertices have unequal sizes. So in this version of the Kernighan and Lin algorithm that we just studied, all of these vertices have the same size, let us say unit size. And now to extend this to unequal sized vertices, we assume that let the smallest element has unit size, and then we replace each element of size s with s vertices. So s unit size vertices which are fully connected with edges of infinite weight. So why do we do this? So that we can feed the algorithm to the original Kernighan and Lin algorithm. This will work, but by representing it as s small unit size vertices, what do? We keep a track of what is the size of the partition on a given side, right? If we represented this whole big vertex of size s as 1, then the partition size would not be correct. The partition size on each side of the partition, the area would not be correct. Hence we represented it as an s-sized clique of where each edge of the clique is of infinite weight. Why do we have infinite weight? So that they will never go into another partition. And then we apply the Kernighan and Lin algorithm on the modified graph. If you want to have k-way partitioning instead of two-way or bipartitioning, let us assume that the graph has k into n vertices, k greater than 2, and it is required to generate a k-way partition, each containing n elements. So what do? We begin with a random partition of k sets of n vertices each, then apply the two-way partitioning procedure on each pair of partitions and on each pair of partitions. So what do? We begin a random partition of k sets of n vertices each, and then apply two-way partitioning procedure on each of these partitions. If we have k partitions, then there are k square pairs of these partitions, k square distinct pairs of these partitions. So begin with a random partition of k sets of n vertices each, and then apply two-way partitioning procedure on each pair of partitions. So, how many distinct pairs of partitions do we have? We have k square distinct pairs of partitions, and therefore the time complexity of one pass over all these pairs is k square n cube, and this will again proceed through a few number of passes. So, we understood three different extensions to the Kernighan and Lin algorithm. With this we come to the end of this module.